SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture number 26 in the course Advanced Robotics. In the last class, we looked at the concept of force control. That is when a robot is interacting with an environment. For example, it is pressing against a hard wall, or there is an impact, it hits an object, or in cases of performing tasks where interaction is involved, for example, using a grinding wheel. In such cases, how do you control forces at the end effector of the robot? And we also saw that although it appears that it's very easy to control forces because essentially human beings can control forces very easily. But in reality, it is not, because there are 12 variables. 6 of them are in terms of force and moments. The other 6 are in terms of linear velocities and angular velocities. And each of these variables are divided into artificial constraints and natural constraints. And natural constraints, you cannot do anything about them. But the artificial constraints have to be controlled, and this is what makes robot control in terms of the force control a very, very difficult problem. Today we'll move on to the next topic, which is multi-fingered robot hands, and after that we'll move on to bipedal locomotion. Now, multi-fingered robot hands is like our hands. We have multiple fingers, we have 5 fingers, and when you catch an object, for example, I'm catching this mouse, okay, and I'm moving it around like this, okay. So the first thing is that in multi-fingered robot hands, we need to see what is the kind of contact that is being made between the finger and the object, okay, because different kind of materials and surface properties would mean that different kinds of contacts are being made. And this basically means that the force and the moments that are being transmitted between the force and that object would depend on things like friction, etc. Okay, so we'll also try and answer the question that how many fingers do you need? For example, do you need 3 fingers, 4 fingers, 5 fingers? Why do we have 5 fingers? Okay. Now, this is divided into 2 parts. One is the grasping, that is, I want to grasp an object. So this is my mouse, and I want to grasp the mouse, okay, using 3 fingers. So it is in, as I was explaining in the last class, initially this is in position control because the fingertip is moving in free space. The moment it is in contact with the object, it is in constraint space. Now I have to move on from position control to force control, okay, and I have to control the forces to grasp the object. That means the object doesn't fall, and I may need to supply forces which are going to manipulate the object. Suppose I want to do like this with this object. So I'm grasping and I'm also manipulating. Now for that you need multi-fingered hands, okay, because you cannot catch an object with 2 fingers and try and manipulate it. You'll not be able to apply all kinds of motion on the object, okay. So today we'll start off our discussion with multi-fingered robot hands, and then we'll move on to the next topic, which is bipedal locomotion. So we start off our discussion on multi-fingered robot hands, and as I was explaining that multi-fingered robot hands, the complete application can be divided into 2 parts. One is I am giving you an object, let's say this cube or a cuboid, and I have multiple fingers, and I'm supposed to catch this object with multiple fingers, okay. So that is one. Now after I catch it, that means I basically need to grasp it so it does not fall. Number 2 is I need to manipulate it. Now, so this is divided into 2 parts, grasping and manipulation. So we'll see, and we'll try and answer these questions like how many fingers are required, what is the fingertip contact, how can you control an object, how can you control the velocity of an object by imparting velocities at the fingertip, and things like that, okay. So let's start off with discussion on multi-fingered hands. Now there are some very famous hands which have been developed over the years, and one of the most famous hands is called the Salisbury hand, which was developed by Salisbury at Stanford University, and it has 3 fingers. So you can see that it has 3 fingers, okay. So there are 3 fingers, and each of the fingers have 3 degrees of freedom, okay. So there is each finger has 3 degrees of freedom, okay. So as a whole, in total, this 3-finger hand has 9 degrees of freedom. So it is 9, 3 into 3, which is 9 degrees of freedom hand, okay. And this can hold an object, like it is being shown here, that this 3-finger hand is holding a nut, okay. Now the 3-finger hand can grasp the nut and it can also manipulate the nut. For example, it can rotate the nut about this axis. Okay. Now, how is the fingers actuated? Or rather, before I go to the actuation, what are the degrees of freedom? So the first degree of freedom, if you can see, is this one. So it is about that axis, 1. This is the second one, 2. And there is one which is orthogonal, which is here. That is my 3 degrees of freedom. Okay, so this is 1, 2, and there is one down there, which is 3. Like this, like this, and like this. So there are 3 degrees of freedom. Now, at the fingertip contact, it is making contact. The fingers are making contact with the object. Now, depending on whether there is friction, there is no friction, whether it is soft or it is hard kind of contact, different kind of conditions will apply. For example, can it apply forces, moments? Can it apply, what are the various forces and moments it can apply, and things like that. Okay. So now the next is, how is this being actuated? Now, in the Salisbury hand, it is actuated by cables. The actuation is by using cables and motors. So you can see that the motors are somewhere at the back, and these are cables which are connecting. Okay, so at each of the joints there are going to be pulleys. So I can explain it this way. Well, I think there is a figure here. Yeah, this figure shows the cable drive of the fingers of the Salisbury hand. So at each of the joints there are pulleys. So this is a pulley now. Okay, and the cables go round the pulleys like this, and they're attached at one end. Okay, and how are they actuated? So this cable will go from here, go around, and then go to the motor on the other end. So this is being connected to the motor. So let's say there is a pulley here which is at the motor. Okay, so this is rotating about like this direction. Now the fingers or the joints of the fingers are actuated by cables which are actuated by motors which are kept at a distant location. So each of the cables, for example, if you look at a let me say this is a cable going through a pulley, and this is a tension, this tension T1 and this is T2. Okay. So when this cable is pulled in this direction, for example, if the cable is pulled in this direction, what is going to happen is this joint is going to rotate. So if the joint rotates, the fingertip is going to rotate. So if I put my fingertip here, okay, then this fingertip will have this kind of a motion. So this is how cable drives work, that there is a tension which is provided at one side of the cable, and then the motor rotates, the cable is pulled, and the corresponding pulley to which it is connected rotates, because of which the joint rotates. So these are basically called cable drive systems, and the Salisbury hand is basically operated by motors and cables. The motors are kept at a distant location, and they are connected by cables to the hand. Now, how many motors are there? There are 9 degrees of freedom. So there are 9 motors, and what we can do is by applying different tensions on the cables, the hand can perform different motions. Okay, so we are changing the angles of the hand by essentially moving the motors which are stretching the cables in a particular direction. Another hand which is very famous is called the Barrett hand. Okay. The Barrett hand has 3 degrees of freedom, has 3 fingers. So this also has 3 fingers, and there are 3 degrees of freedom in each finger. Where are the 3 degrees of freedom? There is one here like this, there is one there which is like this, and there is 1 degree of freedom where the whole base can move along that. So if you can observe, this base can move like this about this axis. Okay, so we have 3 degrees of freedom per finger. So 3 into 3 is 9 degrees of freedom. Okay, so we have a 9 degree of freedom hand, the Barrett hand. Now if I draw a view of it, if you can imagine, these fingers can move in this direction. So if I'm seeing the view from here, what will appear like there is one finger here. So there's one finger here, there's another finger here, there's another finger here, and this finger can move on the base, actually this side. Okay, so this finger can move and come here. Okay, similarly this finger can move this side or that side. The base can rotate. So that is how it changes the position or the location of the fingers, and this has 9 degrees of freedom. It is a very common hand used in industrial applications. Now, something that you can see in the Salisbury hand and also the Barrett hand is that there are 3 fingers, not 5, okay, not 2, but 3 fingers. So we need to answer this question: why are there 3 fingers? Okay. The second is in the Barrett hand also we see that it has 3 fingers and 9 degrees of freedom. Okay. Now let's look at how do we analyze a grasp and how do we do multi-finger manipulation. So there are 2 aspects of this problem that we are facing in this, that we are trying to solve in this lecture. The first is I should be able to grasp. What does it mean? It means that I should be able to, when I have a contact there, I should be able, at that contact point, I should be able to apply forces and moments about an axis. Okay, so I can put a local axis frame. Okay, this is my global axis, this is the axis on the body. I can put another axis there and say that I can apply forces or moments about an axis at the contact point, at contact. Okay, that is for this case. Now, and these are basically called wrenches. So the combination of forces and moments that can be applied at the contact point about an axis is called the wrench. Okay, now of course there has to be contact. If there is no contact, there is no wrench. For example, in this case, there is no contact, okay, between the object and the fingertip. Now in this case, you can apply a linear velocity and an angular velocity at the fingertip. So twists are basically linear and angular velocities about an axis. In this case, the axis is at the tip of the finger. Okay, so here there is no contact, and in case of wrenches, there is contact. So this analysis is basically done based on twists and wrenches. Okay. So if it's possible to apply a wrench, it basically means that you can apply a force or a moment about an axis. Now, how many forces and moments can you apply? So there are three forces, Fx, Fy, and Fz, and there are three moments, Mx, My, and Mz. So in total, there are 6. What about velocities that you can apply when it's moving freely? So velocities again are 3 linear velocities, Vx, Vy, Vz, and omega x, omega y, and omega z. So that is 6 again. Okay. So when there is no contact, we can apply twists. When there is contact, we can apply wrenches. Now, how many wrenches can I apply would depend on the contact conditions. Okay. So what is the type of contact condition? For example, I have an object here. Let's say this is an object, and this is a fingertip, okay, making contact. So depending on the kind of contact that has been made there, okay, this is basically the contact type. What is the meaning of contact type? Is it point contact? Is it making contact on a surface? Is it making contact on a point? Okay. Is there friction or is there no friction? So mu means there is friction at the contact. Minus mu means there is no friction at the contact. So depending on these conditions, you'll be able to apply different amounts of wrenches. So in total, there are 6 wrenches and there are 6 twists. Okay. So depending on the contact condition, you'll be able to apply. So when you're grasping, you should be able to apply some forces, okay, and some moments. So basically, you should be able to apply wrenches. When you're moving an object, you should be able to apply twists. That means you can apply linear and angular velocities about an axis. Okay. So what is a twist? A combination of translational and rotational velocities of the object at the fingertip, which is 3 in terms of the linear velocities and 3 in terms of the angular velocities. What is a wrench? It's a combination of force and moments applied to the object by the fingertip. There are 3 forces and 3 moments. Okay. Now the wrench space in 3D is 6. Okay, 3 forces, 3 moments. Okay, 3 forces and 3 moments. In 2D, it is 2 forces and 1 moment. Okay. So in 2 dimension, it is 3 dimensional. In 3 dimension, it is 6 dimensional. Now, depending on the type of contact that is there, we have to first analyze how many twists or wrenches or twists and wrenches can be applied. For example, if there is no contact, okay, how do we write it? Okay, let us see how do we write this. So if there is no contact, that means you have an object and your fingertip is here now. There is no contact. So you can apply 3 linear velocities and 3 angular velocities at the fingertip. Okay. So we write this as, this is for twists. Please note on the left hand side it is twist, right hand side is wrenches. So T1 is the, this is my angular velocity omega x, this is omega y, this is omega z. This is Vx, Vy, Vz. Okay. So the way we write it this way: omega x, omega y, omega z, Vx, Vy, Vz. Wherever it is possible to apply angular velocity or linear velocity, we put 1. So it is possible. So T1 basically means you can have an angular velocity about the x-axis. T2 means you can have angular velocity about y-axis. How many total? 6. What about wrenches? It's a null space because you cannot apply wrenches because there is no contact. Okay. So this means no contact. Second is point contact without friction. Now, as shown here, you have a fingertip which is making contact like this, if you can imagine. Okay, this is my fingertip, and it is making contact at a point. Okay, that's my axis as shown there. Now, you can see in the figure here that how many, there is point contact without friction. So mu is equal to 0. Okay. Now, if mu is equal to 0, the body is free to move not in the normal direction but in the other directions. For example, if I keep the fingertip here, then you cannot move obviously in that direction, no? So it is constrained. Okay, so this z direction motion, which is the T6 motion, is constrained because it cannot move in this direction. It will have to go through that support. But because there is no friction, it can move this side or it can move that side because there is no friction. Okay. Now, what about moments? Now, it can rotate about this, it can rotate about this, it can rotate about this because there is no friction also. So you can have angular velocities. Please note that we are talking in terms of linear velocities. So these three are angular velocities: omega x, omega y, omega z, and this linear velocity is vx, vy. Vz is the linear velocity which you cannot, vz cannot be applied, so it's 0 because there is no friction. So only the normal velocity component is constrained. The other velocity constraint can, in the other direction, the velocity is possible because the finger can move. Okay, because there is no friction. Mu is equal to 0. So because it cannot move in this direction, you can apply a force. Okay, in the z direction. So this is my x, y, and z direction. So in terms of omega 1, we have 0, 0, 1. This is my fz force. So it is 0, 0, 1, 0, 0, 0. Okay. So how many twists? There are 5 twists. And how many wrenches? 1 wrench only. Okay. So we are seeing that we are having the total 5 plus 1 equal to 6. Okay. So wherever it is not possible to have a velocity, you may be able to apply a force. Okay, that is what we are seeing here. In the z direction, Vz is equal to 0. So you can apply a force there because I can press in this direction and apply a force. That's where this wrench is coming from. Okay, so you can apply a force 0, 0, 1 about the z axis. Okay, so there are 5 twists and 1 wrench. Now the same if you look at point contact with friction. Now mu is there. Okay, now if friction is there, it basically means that if you can imagine that there is a contact here and there is friction, so there is a normal force and there is going to be a reaction force. Okay, so F by N is equal to mu is equal to F by N. Okay, so if you have a force in this direction, there will be a normal reaction in that direction. Okay, so which basically means that the motion is constrained in that direction. So there is no motion in the x direction. There is no linear velocity Vx, Vy, and Vz. It's not there. So this is point contact with friction, where the fingertip is making point contact and there is friction. So mu is there. What motions are possible? The only motion that is possible is that you can rotate about this axis. So you can have an angular velocity. So T1, T2, T3, so omega x, omega y, and omega z are there. Now because mu is there, you can apply a force in this direction. There is a resistance, resisting force in this direction and this direction. So all the 3 forces are possible. Okay. So this basically tells us that all the 3 forces Fx, Fy, and Fz are possible. Okay. So this is in terms of the forces. Omega 1, W1, W2, W3. These are forces in the x, y, and z directions. Angular velocity, can you apply a moment? No, you cannot apply a moment because it's a point contact. About a point, you cannot apply a moment. Now, in the previous case, we saw there was okay. So now, in this case also, we see this plus this is equal to 6. So we have 3 angular velocities which can be applied, and we have 3 forces which can be applied. Total is 6. Now, very often when we are talking about multi-finger manipulation, we make the assumption that it is point contact with friction. Why do we do that? Because it's simple. Okay, because we assume that the robot fingertip is like this and it is making a point contact with friction, so it can resist a force in this direction, and that direction. Okay. Now, very often the robot fingertips have some soft material covering. Okay, soft material as cover on the fingertip. It could be plastic, it could be rubber. Now this is essentially done to increase mu. So to increase the coefficient of friction, we apply this rubber, which increases the mu value there. Also, it is safe for safety. So if you have a metal finger, robot finger, and it is pressing against a soft object, there is a chance it will break. Okay. So what is done is a very thin layer of rubber coating which is put. Now that rubber coating is going to deform, and hence it is called a soft finger contact. So if you can imagine, this is my fingertip contact and this is the contact, so it is deforming there. Okay. Now because it is deforming, first of all, you cannot apply and there it is deforming, plus there is mu. So you can apply a force in this direction, and that direction. So three forces are there. Plus, because it is deforming, it is surface contact now. You can also have a resisting moment there about the z-axis. Okay. So in terms of what is allowed now is you can have a moment about the x-axis and the y-axis. You cannot have a moment about the you cannot have an angular velocity. Sorry, you can have angular velocity about the x-axis and the y-axis, but not about the z-axis. So this is omega x, omega y, and omega z is equal to 0. So there is only two which are possible. In terms of forces and moments, I can apply three forces about the x, y, and z axis. These three are possible. It was the same case where you had a point contact with friction. But now because there is a deformation there and there is surface contact, what is happening, we can also resist a moment there. Okay, so this is my moment about the z axis. So this is fx, fy, fz, and this is omega z. Sorry, not omega z, we can call it mz, which is the moment axis. Now sum of this plus this is again equal to 6. So depending on the type of contact that is there, we have to first find out so let's go back and look at the fingertip again. So depending on the kind of contact that is there, here, for example, here, we need to see what kind of contact is there. Okay, is it point contact with friction? If it is point contact with friction, then it can apply one force. No, sorry, it can apply three forces, fx, fy, and fz direction it can apply, and no moments. Okay. But if it is soft finger contact, we will end up with one moment also, which will become mz. Okay. So depending on how many forces and moments are there would depend on the type of contact there. Now, obviously, what is the point in this discussion? If you're thinking, the point in the discussion is, the point in the discussion here is if you are catching an object using three fingers here, and here. Okay. In that case, you are applying forces and moments at the fingertip here. That is how you're constraining the object, right? So you need to know what is the contact condition, because that determines how many forces and moments you can apply at that point. Okay. So for static equilibrium, this object can have, let's say it has mg in different directions. So you need sigma f x, y, and z to be 0 and moment x, y, and z to be equal to 0. Okay. So what we have seen is that what we see is that for static equilibrium, I need to know how many forces and moments can be applied at the fingertip, and that is what determines whether the object is in static equilibrium or not. Now, if I want to move the object, suppose I want to rotate this about this axis, that means I want to manipulate it. So I have to apply forces, moments at the fingertip in order to achieve that motion. In that case also, I need to know how much forces, moments can be applied at the contact condition. So it is completely determined by the contact condition, the type of contact, and whether friction is there, not there, or whether it is soft. Okay, so now I hope you understand what is the need for this analysis of twists and wrenches, because this is what determines how many forces or moments can you apply at a fingertip to grasp and then to manipulate. To manipulate, you may be able to, you may need to apply velocities. Okay, so this again is a constraint which basically tells us, depending on the contact condition, how many forces, moments can be allowed and how many twists are possible. Okay. So the most commonly used one is point contact with friction, okay, which means there are three forces which can be applied. Now, we talked about grasping. Okay, but grasping is an English word. Okay, now what do you mean by grasp mathematically? Now, by grasping, we can mean that whether the grasp is in closure. What is the meaning of closure? It means that it can resist disturbances. Okay, so what I mean here is that I have a cube. Again, the same example. I have a cube. I want to hold it with 3 fingers. Okay, so I have 3 fingers, one here, another one there, another one on that side. Okay, now this has to resist the weight of the object, plus when it is moving, suppose the robot is moving, there will be acceleration forces, mass into acceleration forces will come, inertia forces will come. Okay, so the inertia forces, corollary centrifugal force will come, and there is a gravity force which is here. Okay. So it has to resist these forces, and hence this is some kind of a disturbance on the system now. So complete restraint and internal forces are basically for restraining the object, how much force is required, and to ensure closure, can it resist all kind of disturbances? That is the question which we are trying to look at. Okay, so not only must it be stable in the sense that when you grasp it, it shouldn't fall off, but it should be able to resist disturbances. Now, even if the rank of the matrix of the screw coordinates is 6, a subset of disturbances acting on the body can be resisted by the grasp. Okay, only let's call this so only a subset of disturbances acting on the body can be resisted by a grasp. Let's look at this example. Okay. So here we are catching the object here, here, and here. Is it stable? What is the meaning of stable? Here stable means can it resist all disturbances? Okay. Now, if you see this, it's very clear that if I apply a force in this direction, okay, what is going to happen? There will be reactions in that direction, and this is stable. So whenever I apply a force like this, like this, like this, these are forces I'm applying on the object or disturbances. It will not, the grasp will not break, or the contact will not break. That means it will still be in grasp because there is opposite and equal reaction from these sides. Okay, but the moment I give a disturbance in the other direction, say for example, if I start giving a disturbance in this direction now, then the box will immediately come out. Okay, this contact will break. That you can imagine, right? That means this grasp of this square object by 3-point contacts, we can say 3 fingers, is stable only for some disturbances. Okay, so this fellow is stable. Okay, but not stable for all disturbances. Okay, and it cannot resist all disturbances. Okay, which means in this direction it's okay, but the moment I do it in that direction, it will come off. Okay, and that is the meaning of what we mean by this type of closure is called force closure. Okay, please note it is called force closure. So closures can be force closures or they can be form closures. So a grasp can be either force closure or it can be form closure. Okay, so there are 2 types of closure. So the first kind of closure is called force closure, where you can resist some disturbances, but you cannot resist all the disturbances. Such grasps are called form closure, force closure. Now, force closure can also be, was first explained by Renault in 1963, where he said that if you hold this object like this, like this, like this, and like this, by three line contacts. So one line is here and the line is there and the line is there. This you might be familiar with in day-to-day life. This is very common for us. Suppose I have an object like this. Okay, you can place your fingers. You can place your fingers such that you can place your finger here. You can place one finger on that side and one more here. Okay, that means it is something similar to what is drawn here. So I'm having 3-point contacts and I'm catching those 3. It's like pinching one here, and one on the other side. It's like pinching that, and you can lift an object or you can grasp an object. Okay, and this is stable only if the force is in this direction now. Okay, so if it's pressing against the contact, then it is stable. But the moment the disturbance comes in the other direction, okay, suppose I force it in that direction, it will immediately break. Okay, so if in this case, if I force it like this, the grasp will come off. Okay, this is basically what we mean by a force closure. So it can resist a small subset of forces of disturbance forces. Okay, Now this is basically called force closure, and this was initially found by Renault in 1963. Now the other type of closure, now why does this happen? I just missed a point. So why does this happen? Now it basically happens because the forces you see here are unisense. This is a point I missed. Please note, very, very important. These forces are unisense, means unidirectional. Okay, these forces are unidirectional. That means they can only, if there is a force in this direction, it can give a reaction. This contact here cannot, this contact cannot produce a force in that direction. Okay, similarly, when the object is holding, look at this example here. When the object is being held by a three-finger hand, the fingers can press there, but the finger cannot apply a force in the reverse direction. Okay, that you should be very clear from, and it's very easy to understand that. So if I look at the example here, okay, suppose I place an object here like this. Okay, this is an object. At the contact point, the finger can apply a force in that direction. That's okay, but the finger cannot apply a force in this direction because it's a unisense force which is being applied, or unidirectional force which is being applied, unidirectional which is being applied, and because of which we end up with this condition of force closure. Now, so the other kind of closure that can resist all kind of disturbances, basically what we call form closure. Okay, now if the collection of wrenches, bidirectional, unidirectional, acting on an object can resist arbitrary disturbance wrenches, then it is supposed to be form closure. And this was found by Lakshminarayan in 1978. Okay, so he observed that for 3D objects, you need 7 point contacts without friction to have form closure. Okay, say for example of form closure, if I say in 2D, let me take the example of 2D here. In 2D, suppose I have a rectangle like this. Okay, then the question is, in order to resist all disturbances, how many fingertip contacts do I need without friction? So I need one here, one here, one here, one here. So that means I need 4. Okay, so 4 point contacts without friction are required for form closure in 2D. Whereas in 3D, you need 7. This is point contact without friction. Okay, now if you have seen this, if you have thought of this, we could have also had the finger placement like this. I could have placed the finger here, 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 and here. That's also form closure. But you cannot have this closure with less than 4. Suppose I have only 3. What will happen is, because there is no friction here, so this can only apply forces like this, like this. So this side is fully free. So this object can move in that direction. So if there's any disturbance like this, the object will move. Whereas the moment I put a finger here, what is going to happen is it will get locked, and sorry, if I put a finger here, it will get locked, and now irrespective of which direction disturbance you give, it is locked now. Okay, the object will not move. So Lakshminarayan was the first who showed, you can prove it very easily actually by looking at conditions of sigma fx y z equal to 0 and mx my mz equal to 0. From this we get this condition and this condition. So for point contact without friction, you need to have 7 point contacts for holding a 3D object in form closure, and for 4 point contacts in 2D are required for form closure in 2D case. Okay, please note that. Okay, now we talked about grasping. Now grasping forces are required to just maintain the grasp, and these are sometimes called internal forces. So 2 fingers having point contact with friction constraining an object, particular solutions. So we have let's say we have point contact with friction. So this is an object. I might have explained this in some other context in one of the earlier lectures. So I have 2 contact points and I have friction, so I can apply friction like this. So it is fx1, fx2, fy1, fy2. This is my x-axis, that's my y-axis. Okay, now suppose there is a disturbance force which is acting there. Let's say the weight of the object and disturbance, whatever. This is 2D case. So disturbance is fx, fy, and mz. These three are possible, right? Because it is a 2D case. So in this case, if I write for static equilibrium, so let me say 2D case, 2 fingers, point contact, no friction. So this basically means, with friction, point contact with friction. Because there is friction, there is this normal reaction. Otherwise, there will be no normal reaction. Now, for static equilibrium, what do we do? For static equilibrium, sigma fx, fy, and fz is equal to 0. Okay, and mx, my, mz equal to 0. Okay, so for static equilibrium, this condition has to hold. So which means sigma fx equal to 0 means forces in the x direction are equal to 0. So if I write fx, fy, and mz here, then what do we get is I get this matrix 1 0 1 0 0 1 0 1 1 0 minus 1, and this is fx1 fy1 fx2 fy2. Okay, how did I get this? So sigma fx is equal to fx1 plus fx2 in the x direction. So sigma fx equal to 0 gives me this equation. So there is a force fx is there in the x direction. There's fx1 and fx2. So fx must be equal to fx1 plus fx2. Don't worry about the sign. Signs get automatically adjusted. So I can write this as f is equal to w into c. Okay, so I can write this as w into c, where c is this matrix, w is this one, and f is this one. This is a 2D case. In 3D also exactly the same thing will happen, only this matrix will become 6 by 8. Here it is 4 by 4. Okay, so now I'm writing this as f is equal to c. Now what I need to know is I need to find c, fingertip contact. Fingertip forces required to grasp an object. That is the objective of this. That means I want to grasp this rectangular or square object. How much fingertip force is required? Suppose this is from here to here, length is 1 unit, length is 1 unit. Okay, so the question is, what fingertip forces are required to grasp this object, which means essentially I need to solve this equation. Okay, so f is equal to w into c. So what I need to know is I need c, which is the fingertip force, and this is equal to w hash into f plus w into w hash minus I into lambda. This comes up as C particular solution plus C homogeneous solution, Cp plus Ch. Okay, so this is the generalized solution. If you note, in case you didn't note, this is a 3 by 4 matrix. Okay, so this is a 3 by 4 matrix. So if you want to take the inverse of this, you have to find the pseudo inverse, where W is given by the pseudo inverse, where W hash is the Moore-Penrose pseudo inverse. Okay, now the solution for C has two parts. One is called the particular solution, that is this part, and the second part is called the homogeneous solution, okay, which is in the now this part is in the null space. Is also called the orthonormal basis. Now I think I've explained this in one of the earlier classes. If you have an exact inverse, then W into W hash will be equal to I. Sorry, if W into W, if there is an exact inverse. Now if there is no exact inverse, then this implies that W into W inverse minus I is not equal to 0. Okay, sorry, if there is an exact inverse, it is equal to 0. But in this case, because W inverse is not exactly equal to, this is a pseudo inverse, it's not an exact inverse. Okay, so there is going to be some error here. So I'm writing this as W into W hash minus I is not equal to 0. Okay, that is this part now, because this is not an exact inverse. Now what is lambda? Lambda is a positive constant. Lambda can take different values, and for which you'll get different solutions. Now, if you go back and think a little bit, what is the solution to this problem? Is there are infinite solutions actually. Because if you say that you want to grasp an object having a weight of say 2 kg, then you can say you can apply fingertip force of 1 kg, 1 kg and multiples of that. And that multiples of that is exactly what is coming from here. Okay, so if I just give the example here, so this is my mg, suppose I say that is 10 Newton. Okay, so you need to catch it, you need, if mu is equal to 1, I'm assuming, you need 5 here and 5 here, because there is a 5 there and there's a 5 there. Mu is 1. Okay, so to catch this object of 10 Newton, you need 5 Newton and 5 Newton, or multiples of 5 into lambda. Lambda can be anything, it can be, lambda has to be more than 1. So basically what we are saying is lambda is a positive constant, which means you have multiple. What are the multiples possible here? You can have 7 and 7, you can have 8 and 8, you can have 10 and 10. It's infinite actually. If I apply 10 Newton here and 10 Newton here, it will still grasp, because the minimum is 5 and 5. Others are all multiples of that. Okay, now this is what it means, that there is a constant there which can give us the multiple solutions. Okay, now C is equal to Cp plus Ch. This will come in your null space. Okay, so this solution belongs to the null space, and this is called the, or this is also called the orthonormal basis vector. Okay, so this full solution is made up of two solutions. One is this part and the other is that part. Okay, now for grasping, the forces that are required are also called internal forces. The basic forces required for grasping. Okay, that means without these forces you cannot grasp. So let's go back and try and see this. If fx1 and fx2 become equal to 0, it basically means that there is no force. That means you cannot grasp. That means this force and this force cannot become 0. Okay, they have to be there irrespective of anything. Irrespective of what means, even if this becomes 0, okay, then also this fellow cannot become 0. That is an interesting, something very interesting. That even if the external force becomes 0, that means this part becomes 0. So your Cp becomes equal to 0. Ch is always not equal, is never equal to 0. Okay, because it's basically something like an error. Error of what? Error because this is not an exact inverse, so there is some error there. Okay, an error into lambda is the solution, and this is basically called internal forces. So which means they are going to be non-zero, and they are going to be there in the null space. Means you cannot measure them. Okay, so you cannot directly measure internal forces. So if I want to now manipulate an object, I come back to my original problem. I have an object here, and I have a finger here, I have a finger there, point contact with friction. I want to move this object in this direction with some velocity, 1 meter per second, just for example. So this involves two steps. Number one is grasp. That means there has to be some internal forces. There has to be some internal forces just to grasp. That means this force and this force is required. Plus I want to move in this direction. So additional force is required to move the object now. That is, to manipulate the object, you need additional forces now. That means the total force would depend on internal forces, internal force plus manipulation force. Okay, so the total force that the fingertip has to apply will depend on the internal forces that are required for grasping and the manipulation forces that are required for moving the object in a particular direction. Okay, I hope this concept is clear, that the total force that is required is actually broken up into two parts. One is just for grasping it. That means you require the internal forces, and then you need forces above the internal forces, which are going to give you which is going to impart the velocity to the object to move it in a particular direction. Okay, now let's look at a problem to understand this better. So here, this is an object. So this is my object. Okay, it is constrained by 1 point contact. Okay, so this is my 1 point contact This is my point contact finger, is constrained by one finger which has point contact with friction, and the other one is soft finger contact, and one soft finger contact. This is an example. Okay, so if there is point contact with friction, there will be three forces. Okay, so three forces. This is my point contact with friction. The other side, if there is a soft finger contact, okay, soft finger contact will three forces plus one moment that we have seen. So there are three forces and one moment there. Okay, let's look at now. This is a case where we have two soft finger contacts. The object is constrained by two soft fingers now. Soft finger would basically means there are three forces and one moment. Okay, so let us go back and see. So this is the problem. Now let us write down. So this is my object. So we are given the x-axis, y-axis, and the z-axis directions. The z-axis is pointing outward like that. That's my z. So x, y, z. Now omega 1, omega 3, and omega 4. Sorry, not omega. Let's call it w. So there are three forces there. Okay, we are just naming them w1, w4, and w3. On the other side, we have three forces, which is w2, w5, and w6, and we have one moment, which is w7. Okay, so this is a moment about the x-axis. Okay, now I want to write this equation. I want to write the force balance equation. So for that, what do we need to do? I have to do sigma fx, y, and z equal to 0, and sigma mx, y, and z equal to 0. Okay, so in that case, let's try the first equation, sigma fx equal to 0. So what are the forces in the x direction? So if you look at this figure, what are the forces in the, there is one force here, there is another, which one is here? W2 is there. These are the two forces in the x direction, and there is an fx there. Okay, so when I write my equation, F is equal to W into C. C is the fingertip forces. How many fingertip forces? There are 7, right? So on this side, it will be W1, W2, W3, W4, W5, W6, and W7. Okay, and this on here is my Fx, Fy, Fz, Mx, My, and Mz. That's the full equation. Okay, now this matrix is the W matrix. So the first line would mean sigma Fx equal to 0. What are the forces in the x direction? W1, this is W1, and W2 there, this is W2. So on this side it is W1, W2, W3, W4, W5, W6, and W7. Right? That's how I get this one. Next is forces in the y direction. So what are the forces in the y direction? If you just look at this, this is y direction. So Fy is there. This Fy is equal to W3 plus W5. So this is a W3 and a W5. So 1, 2, 3, 4, 5. So this is 3 and 5. Right? So proceeding like this is for forces and this is for moments. What is the moment about the x-axis? Mx. So if you look at the moment about the x-axis, where is the x-axis? Is this one. I want this moment. Okay. What are the forces that are causing this moment about the x-axis? Okay, so moment about x-axis is being caused only by W7, which is this one. What about moment about y-axis? Moment about y-axis is this one. So this moment is caused by W3, and this side is W5. Okay, so this can rotate. Sorry, W is not is the one that is coming outward to the board. So it is like this moment which is being caused. So it is W4 and W6 because it is coming outward like this. Okay, this is causing a moment about the y-axis. So it is W4 and W6. So this is my W-axis, W matrix. Now I have written F is equal to W into C. I want to find what is C. I need to take the inverse of that. So let me write it here so that we understand better. F is equal to W into C. I want C. C is equal to W hash into F plus W hash into W minus I into lambda. Okay. And this would basically mean that this is my homogeneous solution. Okay. So this homogeneous solution is in the null space. So this basically means that I will need the internal force, which is the orthonormal basis vector. Okay, orthonormal basis. Now if you look at the previous figure, which force is required here to maintain the grasp? That means all other forces can become zero, but that force cannot become zero in terms of the grasping. Otherwise the object will fall. Okay, so in this, which forces are required? Those are the internal forces without which this object cannot be grasped. Okay, so if you think a little bit, you require this one and you require this one force this side, one force this side, without which you cannot grasp. Okay, this grasp is not possible. So if W1 and W2 are to become zero, then this object will fall. Okay, so from this, the orthonormal basis vector is this W1 and W2. So the orthonormal or the internal forces are 1, 1, 0, 0, 0, 0. This is my internal forces. So the internal forces are always positive, and the graphs can be maintained against arbitrary disturbances. Okay, so this basically means that we are having internal forces which are given by. Now if I look at the second question, problem that we're looking at, I hope this is clear to you. What is an internal force and why is it required? So just to hold the object, not to manipulate it, you will always need this force and this force. The other forces are required to manipulate the object, to move it around. Okay, now let's look at this example. This is also an example of an object that is being held by two soft finger contact. So the moment you say soft finger contact, it basically means that there are three forces and one moment. Okay, three forces and one moment. Now on either side holding it. So if you can imagine, there is a fingertip here like this, there's another fingertip like this. Okay, and the contact condition there is soft finger contact. So how many forces and moments? Three forces, one moment can be applied on either side. Now let us see, this is W1, W2 in the X direction. In the Y direction we have W3 and W5. This is the Z direction, that Z is out of plane. So Z would be in W4 and W6. Okay? Now so this is Fx, Fy, Fz. Now what about the moment? So there is a moment W8 about this axis and W7. So there are two moments there. Okay. Now I want to write my equation. F is equal to W into C. Now C is how many? There is 4 here and 4 there. So it is W1 to W8. Okay, so if I write it here, W1 to W3, W4, W6, W7, W8. Okay, and on this side it is Fx, Fy, Fz, Mx, My, Mz. Okay, now I have to fill in this matrix W. Exactly in the same way we say sigma Fx equal to 0, all forces in the x direction are equal to 0. If I do that, then what do I get? This force W1 is there, W2 is there, and Fx is there. So Fx, W1, W2 is this matrix. Similarly, in the similar way, I can fill in the other elements of this matrix. Okay, and I get my W matrix. Now please note that this is 1, 2, 3, 4, 5, 6, 7, 8. This is an 8 by 6 matrix. This is also non-square. So if I want to find, my equation was F is equal to W into C. If I want to find what is C, then I need to take the inverse. And if I take the inverse of that, I will get, so if I take the inverse of this, what I'll get is, the solution will be C is equal to Cp plus Ch, and Ch will have internal forces. So the question here is, what are the internal forces here which are in the null space? Now if you look at this problem, like in the previous case, you cannot maintain this grasp if you do not have this force and this force. That is one. That is this one. This force is required. But now there is a moment also. Okay, that means you also need this moment and that moment. So this is the forces and this is the moment. Okay, so this is giving you W1, W2, W1 and W2, and what moment? W8 and W7. Okay, so now the null space has two internal forces. One is a force, the other is a moment vector. So what we have seen is that this basically gives us the idea. So what we today looked at is that if you want to grasp an object and you want to manipulate an object, then first you have to grasp it, and in order to grasp it, you must have internal forces. The internal forces maintain the grasp. Okay, and then after grasping, you can then on top of that apply more forces to manipulate an object. So it looks very easy that you grasp an object like this and then you manipulate it around like this. Okay, but there is no robot in the world which can actually do like this. And yet human beings can very easily, I can catch a pen and I can do like this. Or I can catch this computer mouse and I can simply do this. Okay, but there is no robot which can do that. Why? Because you need to have control of the internal forces, and then on top of that you need to apply external forces such that you have the particular solution plus the homogeneous solution, and both of them combined will give you the motion. Now we looked, when we studied force control in the last class, you saw that even to control force in a particular direction is very difficult. And here we are trying to control 3 forces, 3 moments. Okay, and at the fingertip, if there are 8, then you're trying to control 8 components, okay, of the fingertip forces, which makes it extremely difficult. So it's very easy to say that a robot will do like this, but as of today there is no robot which can actually do like this, because we cannot do force control of so many forces. Okay, and if you cannot do, then you cannot grasp and manipulate. So this problem is a very complex problem. It looks simple, but it's extremely complex in terms of mechanics. And in the next class, what we'll look at is, if I want to manipulate the object, that means I want to give a particular velocity. I'm moving this object with some velocity. So I have to give some velocity in my fingertip, and the resultant of that is going to be a resultant velocity of the object. So what is the relation between the fingertip velocities and the object velocity? Okay, that is something we'll be looking at in the next class. So today we'll stop here. Thank you.